Welcome friends to the Formula Engineering classroom, and in this lecture we will understand the concept of buoyancy and flotation. So buoyancy basically defined on the Archimedes principle. So what is the Archimedes principle? So Archimedes principle states that when some body is submerged in a fluid, then that body displays that particular amount of fluid, and the weight of fluid displaced by that body will be exactly equals to the upward force acting on that body, and that upward force is termed as buoyant force. So to understand the Archimedes principle, we will use our previous knowledge as according to the fluid mechanics, and as we discussed the hydrostatic law and the Pascal's law, and the use of that knowledge we will try to understand the concept of Archimedes principle, and we will understand what is the buoyancy and what is the flotation. Okay, so let's try. So let's suppose if we are saying this is our free surface of fluid. So again we are considering this is a free surface of fluid here. Here is the level of this one, and let's suppose we are considering a fluid element in this fluid. So let this is our fluid element. Sorry, this is our fluid element. Okay, so let I'm considering the height of this fluid element is h, and at cross section area we are saying this is a, and let's suppose the top face of this fluid element is at a distance y below the free surface of fluid. Okay, now so as our previous information, we know that is according to hydrostatic law the pressure will be equals to rho g h. Okay, now so I think that is let I'm saying this is rho g y, rho g y. So from this hydrostatic law we can easily tell what is the pressure intensity at this top face of this fluid element. So obviously this is at a distance y below from the free surface, and let's suppose we are saying rho is the density of this fluid. So in that case the intensity of pressure at the top face of this fluid element will be rho gy. Okay, so we can draw it like that. So this will look like this one. So this value will be equals to what? This value will be equals to pressure is equals to rho g y here. This is according to hydrostatic law. And now according to Pascal's law, we know there is a pressure intensity at a point in all directions remains same in the static fluid. So at this point, the pressure intensity will also, that is this pressure intensity will also be equals to rho g y, because this is at the same point here. And as the top face has the same distance, or every point on the top face has the same distance from the free surface, that is equals to y, the pressure intensity on the top face of this fluid element will always will be same. That will be equals to what? That is equals to rho g y. So we can draw like that. And so this is the pressure intensity here. We are simply saying, and on the top face it is same everywhere. So this is uniformly distributed over here. Okay, now so as we are moving down here, so depth increases. So obviously the depth increases, the pressure intensity also increases, because the pressure intensity is directly proportional to the depth in the fluid. So here the pressure intensity will be this much, and what will be the value? So here at this point the depth is y plus h, because h is the height of this fluid element. So we can say that here the pressure intensity, and I'm saying p dash, this will be equals to rho g y plus h. Okay, I think there is no problem in this case. According to hydrostatic law, the pressure intensity at the lower face of this element is rho gy plus h, and according to Pascal's law this pressure intensity will be same in this direction also at the same point. Now again, every point on this lower face has the same distance from the free surface, so the pressure intensity at the lower face will be same. That will be equals to rho gy plus h here. So we can draw it like that. Okay, in this direction also it's look like this one. Diagram is going to be congested here, so I'm not drawing too much arrows here. Okay, so this pressure intensity is how much? This pressure intensity P dash is equals to rho g y plus h here. Okay, so I think there is no doubt here. So as the pressure is uniformly distributed over here on the top face, that is equals to rho gy, we can easily calculate what is the force exerted by this pressure on the top face of this fluid element. So we know the area is A here, pressure intensity is P here, that is rho gy, and that is all the same. So we can directly multiply this pressure intensity to this area, and we can write, let if I'm saying this one is FV1. Okay, so we can write FV1 will be equals to P into area. And what is P? P is rho gy into area. And obviously this force is acting in downward direction. Okay, similarly we can calculate the force exerted by the pressure intensity P dash on this lower face. So that I'm saying this is equals to FV2. So I can write FV2 is equals to P dash into A here. Okay, so what is P dash? P dash is actually rho g y plus h, that is the pressure intensity, into A, and this is acting in upward direction. So obviously from here you can say that is this FV2 is greater than FV1. We can easily say that is FV2 is greater than FV1 because P dash is more than P here. Okay, so and the area is same here, so as the P dash is greater than P here, we can say that FV2 is greater than FV1. Okay, so let's check what is the net vertical force that is acting here. And I think this force will act in the upward direction because FV2 is greater than FV1. So we can say that FV net. So FV net will be equals to FV2 minus FV1 here. Okay, so we can write this is rho g y plus h into A minus rho g y A. So from this one we can say that this value is rho gy a, this is rho gy a, this is going to cancel out, so remaining terms is only rho g h a, and this will act in upward direction. So I think we can write rho g is what? Rho g we can write specific weight, that is W, into h into A. Okay, this is acting upward direction. Okay, now as we are considering this is the fluid element, so obviously it has some weight, so that weight will be acting in downward direction. Okay, let us say this capital W, this is capital W. Okay, so what is the weight? So weight we can calculate by using specific weight of fluid, that is small w, into volume of this element. Okay, specific weight we are writing W, volume is, I think, area is A, height is h, so we can write this is A into h. So this is acting in downward direction. You can notice here the net vertical force FV net that is acting in upward direction is WHA, and the weight of the fluid element that is acting in downward direction is also WHA. Means from here we can say that is weight of the fluid element is equals to the FV net. This is acting in upward direction, this is acting in downward direction, and they are equal. That's why this fluid element is in equilibrium state here. It is not moving upward, it is not going downward here. Okay, because in this case The weight of the element and the vertical force that is acting in upward direction is same here. Now let's suppose we are removing this element from here, and this volume A into H is empty space here. There is nothing here. Let's suppose we are considering. So as this is a void, or this is a free space or empty space in this case, so the weight in this case will be 0. Okay, because there is nothing here, so the weight in this case will be 0. But the vertical force will be equals to Fv net, because this is due to the surrounding fluid around this empty space. So as there is no balancing force for Fv net here, because W is 0, we are considering nothing is here, so W is 0. So the net vertical force is acting in upward direction. So in that case, this will start, this void or this empty space will start to move in upward direction. And actually in that case we can say that this Fv net is nothing, it's simply the buoyant force. This Fv net is equals to the buoyant force. So buoyant force here, and this will acting in upward direction. Okay, and the value of this buoyant force, as I told you, that is according to Archimedes principle, this force will be exactly equals to the weight of fluid displaced by body. Okay, so this buoyant force will be equal to the weight of fluid displaced by the body. So if we are considering this is a fluid element, and this fluid element is displacing some fluid weight here, so actually that fluid weight is exactly equal to W of this one, and that will be equal to WAH. Okay, so let's understand this one more here. So if as we are I'm saying, as there is nothing here, and this is the empty space, in that case the W is 0, so this is the empty space here. So actually this free space is displacing this much of volume of this fluid, that is equals to what is the volume that the free space, or that is empty space, is displacing here of fluid is A into H, and weight of this volume is what, as the W is the specific gravity, sorry, specific weight of this fluid in that case, and A into H is the volume displaced by this empty space here. So the weight displaced by this empty space here will be equals to the specific weight of fluid into the volume, that is exactly equals to this one, that is WAH. Okay, so according to Archimedes principle, when the body is submerged in a fluid, in that case a net vertical force will act on that body, that will be exactly equals to the weight of fluid displaced by that body. Okay, so now that we are considering that this empty space, in place of this empty space we are considering that there is some wood here. So in that case we are saying that W of wood we are considering here. Okay, so this is what, this is the specific weight of this wood, and the volume of this wood is equals to what, this is equals to A into H. Okay, so now again one more thing we are considering here, that is specific weight of wood we are considering is less than the specific weight of fluid. We are considering, this is our first case, we are considering this one, that is specific weight of wood is less than the specific weight of fluid. So the weight of the wood in this case, that has a volume of A into H, so we can write here that is weight of wood will be equals to what, so we can write specific weight of wood into volume, that is A into H. Okay, and as this is the weight, this will act in downward direction. Now, and how much weight of fluid this one is displacing? So I think the volume of fluid displaced by this body is exactly equal to the volume of this wood itself. But as we are talking about the weight of fluid, so in that case we will take the specific weight of fluid here. So we can say that there is, sorry, this FV net, that is nothing, it's equals to weight of fluid. It will be equals to specific weight of fluid into area into height, and that is the buoyant force, and buoyant force will always act in upward direction. So this is acting in upward direction. So you can notice here, as we define that is specific weight of wood is less than the specific weight of fluid, so obviously weight of wood will be less than the weight of fluid, because I think here the volume is Ah and here also the volume is Ah, so this is the same. But as this specific weight of wood is less than the specific weight of fluid, so we can write here that is weight of wood will be equals to weight of displaced fluid. So means this net upward force, this is the upward force, this is the downward force. So the upward force is more than the downward force. So what is the net upward force is acting? So we can say that there is FV net. Remember, this FV net is different from this FV net. And in this case, I'm saying what is the net vertical force is acting on this one. So we can write this will be equals to the weight of fluid minus the weight of wood here. Okay, so this is the net force that is acting vertically upward direction, and due to this net vertical force that is acting in upward direction, this wood will start to move in upward direction, or it start to rise in this fluid, because the net vertical force is acting here, that is in acting in upward direction. Now, so as this element is moving upward direction, the height of, no, sorry, the depth of the face of this top face of this wood is going to be decreased, because as this is rising here, y is going to be decreased. So as the y decreases, the pressure intensity also decreases. But in the same amount, the lower pressure intensity also going to be decreased, because here also y is decreasing. So as this is y is decreasing and this is also decreasing, so both the pressure intensity that is on top face and bottom face are going to be decreased, but the net value, that is FV net, this FV net remains same here. Okay, now let's suppose the top face is exactly at the free surface. So let I'm drawing this side. So let I'm saying this is the free surface here, and this element is here. Also not element, this is the wooden block is here. Okay, now the pressure intensity at the top face of this wooden block is 0. The height of the block is h here. So the pressure intensity at this point or at the bottom face will be equals to what? So I think this will be equals to rho g h. Okay, this is rho g h, and as A is the area, so the vertical force that is acting here, so FV2 will be what? So this will be equals to rho g h into A, or this will be equals to WHA. And you can notice here the FV net, as I'm writing this is that FV net is actually nothing, it's FV2 minus FV1, and here FV1 is what? Here FV1 is 0, because there is no pressure intensity here, so there is no value here. So FV net is, this term is 0, so FV net in this case is going to be equals to FV2, that is equals to WHA. So you can notice here FV net is again WHA. So when this wooden block is rising in this fluid, the pressure intensity of the top face and bottom face are going to be decreased, but the net vertical force remains same up to the point when the top face of this wooden block is exactly at the free surface. But after this point, as the upward force is more, as we discussed here, because the weight of the wood is less than the weight of fluid here, So net vertical force is more here. Okay, so let I'm presenting this one with small f, so there's no confusion here. So let I'm again drawing here. So as this FV net is greater again here, so it will push the block outside the fluid. So block is now here. Okay, height of the block is h here, area is a here. So let's suppose if I'm saying this is h dash. H dash is the height of the block that is submerged in this fluid. So obviously h dash is less than the h. So here FV2, that I'm saying FV2 dash, it will definitely less than the FV2 in this our case when the top face of this wooden face is exactly at the free surface. Okay, because the height of the block in the fluid is going to decrease, so the pressure intensity at the bottom face of this wooden block is also going to be decreased. That's why the FV2 is going to be decreased. So as the FV2 is going to be decreased, so we can say that that is the fluid weight of fluid displaced by this wooden block is also going to be decreased as this is moving out from the fluid. So as the weight of fluid displaced by this wooden block is going to be decreased, at some particular point that weight of fluid that was displaced by this wooden block will be exactly equals to the weight of this block here. So in that case, when the weight of fluid displaced is equals to weight of wooden block, and then it will maintain an equilibrium position, and then this condition is the condition of floating. In that case this will float here. Okay, now so this was our first case. If I'm saying, let's second I'm considering now, if in place of wooden block there is some steel block of same volume, so we can easily say that there is W of steel is greater than W of fluid. Okay, when this is the completely submerged and we are considering in place of wooden block, now we are considering a block of steel here. So in that case the specific weight of the steel will be greater than the specific weight of fluid. So in that case the weight of steel block will be greater than the weight of fluid displaced. Okay, in that case the weight of steel block that is acting in downward direction and weight of fluid displaced, actually that is the buoyant force that I'm denoting by the use of F suffix P, buoyant force, and that is acting in upward direction. So in that case the weight of the steel block is more and than the buoyant force. In that case that steel block is going to sink down in that fluid. Okay, when the weight of steel block is greater than the weight of fluid displaced by the steel block, in that case that steel block is going to be sink down in that fluid. So by considering all these cases we can conclude three cases here. So let's conclude me this one. First I'm saying, let if I'm using the notation like that, if I'm saying W is the weight of block and FB is the buoyant force, so first case I'm saying if W is greater than FB, that is the weight of the block is greater than FB, then the body is going to be sink in that fluid. Second, we can say that if W is less than FB, that is buoyant force, then that body will rise in that fluid. And if we are saying that is that block weight is exactly equal to the buoyant force, then as we discussed here, in this case, when weight of fluid is placed and weight of fluid was equal, it will float. Okay, I think the point is clear. In next lecture we will understand more concept and we will solve few problems. Till then, take care of yourself, and please guys subscribe the channel, comment your doubts, share the knowledge as much as you can, and thanks for watching.